Okay, so to review, we're looking kind of up at the knob. We have our 3 alpha beta dimers, so each in a different color here. We have that gamma piece of the rotor, and we talked about the fact that the different sides have different components, different shapes. They will affect the conformation in these other pieces. All right, so then let's talk about what happens. It turns out that these catalytic subunits, so the alpha beta dimers, can exist in 3 different conformations. Okay, the open, the loose, and the tight form. And let's just follow it over here on the left. So we're going to follow the purple, so the segment at the top, but they would all go through the same steps. So when this is in the open form, symbolized by that O, the ADP and phosphate can enter. So when it's in the open form, essentially nucleotides can bind to or be released from that subunit. And then picture what happens. So the rotor starts turning, and so our rotor is spinning and spinning and spinning and spinning. And when I talk about that, actually, let's go back up here real quick. So really what's spinning is this C-ring. That's what I should say. The C-ring is going to spin and spin. That's going to affect our rotor. But our rotor, remember we said, moves and jumps. So our C-ring is spinning, 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 spinning. And finally it builds up tension and this jumps over 120 degrees and now it's pointing over here. So the one it's pointing to is the O. But now that purple, remember I said we were going to follow the purple. Now it is faced with a different side. Okay, so it's right here. Whatever shape is on the edge of that, it's faced with that. That changes its conformation. It's now in the L form, and that traps those nucleotides. So up here it was open, but now those nucleotides are trapped. Okay, our C-ring is spinning, 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 and finally enough pressure builds up and this pops over another 120 degrees. So now this one is the open, and since we're following the purple, a different side of that gamma subunit, okay, with a different shape is up here. That affects the conformation, the shape of that alpha beta dimer, and it's now in the T form. Okay, at this point, this is where the ADP and phosphate react and form our ATP. And then our C-ring is spinning, 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 and finally this jumps around. Well, remember we said when it's in the O conformation, that's when nucleotides can enter or be released. Well, now this one had ATP, so it is released, and we would start over. A new ADP and phosphate could move in. Okay, so for every 360-degree turn, we're releasing 1, 2, 3 ATP. All right. So let's look at the proton motion across the membrane that drives this rotation of the C-ring. All right, so we need this to move the rotor that moves the, or that changes the various conformations of our alpha beta dimers. Okay, so we know where the active site is. It's on those beta pieces of those alpha beta dimers. We know how the structure-function relationship of that rotor spinning causes conformation changes to the active site to allow the reaction to occur. So what we want to talk about now is how the flow of protons across the enzyme causes this to turn. So protons are going to enter, when we look here, this purple piece. Okay, that purple piece is the A subunit. Get the purple here, there we go. All right, so here was our A. And that subunit has 2 water channel. So the protons can come in. So notice at the top we're in the inner membrane space. Okay, at the bottom we're in the matrix. And protons can come in through this water channel here. Let's highlight or just point that out. So here's this channel, but it only goes halfway through that A subunit. And then we've got another water channel over here that only goes halfway through, but is open to the matrix instead of the intermembrane space. Remember that protons are not free in solution. We don't actually have just H+. What we have is H3O+. All right, they're bound to water. We have that hydronium ion. Remember that our proton concentration, because we built it up with our electron transport chain and all those pumps, our proton concentration out here in the inner membrane space is higher than it is down here in the matrix. That means that the gradient wants to push these H+ through, but again, our channel only goes halfway, so it can't push them just directly all the way through. I also want to review our idea of a weak acid. So if we have a weak acid, which we often symbolized with HA, we know that that can react with water, and it's a weak acid, so it'll donate a proton. So we get A- and H3O+. And then I want you to remember Le Chatelier's principle. If I increase the amount of H3O+, I would expect that to drive this reaction back to the left, right? So if we increase the concentration of H3O+, drives reaction to left. So it means that our acid would want to be more in the protonated, more acid in the protonated form. I can spell, here we go, more protonated form, HA. If, on the other hand, we have a lower concentration of H3O+, if I remove some H3O+, now that's going to pull the reaction to the right. And instead, we're going to see that acid exist as A-. So the gradient's going to try to drive these protons through, but they can't go straight through. But we do have this, this change due to these H3O+ concentration. So importantly, at the halfway point on the C pieces, so on the blue, okay, on the C subunits, and let me use a different color. I wanted like a bright blue, this will work. On those C subunits, we have either, so right around this middle area, we have either a aspartate or a glutamate residue. Okay, so not in the A piece, but back in the on each of these. So here, maybe I should have used a different color, shouldn't I? Here and here and here, somewhere right around that halfway point. Okay, we have these acidic residues. Okay, that C unit, remember, is buried in the membrane, so we've got our membrane here that this is all a part of. And what can happen is that the H+, the hydronium ions, can move in here and get close to those aspartate or glutamate residues. All right, let's look at what that looks like overall. So again, we've got our intermembrane space above. We've got our matrix below, higher concentration of protons. So when we look at this, and I'm just going to rewrite this over here because it's important, we've got our equilibrium, HA plus water, going to H3O plus, and A minus. So if I look at this top left picture, okay, the H plus would like to go across, but there's no direct channel. The residue in the subunit, so that glutamate or aspartate, will either be in the HA form, right, protonated, or in the deprotonated form. So if you look on our picture, we have some that we're showing with a minus, that's showing the deprotonated, and some we're showing with an H, that's for the protonated piece. So when you look in these little circles, those are both minuses, but there's one that has the proton. Okay, so as the H plus moves down here, remember we have a really high hydronium ion concentration, right? And so that is going to push this equilibrium back towards those acids chains wanting to take a proton, want to pick up the proton. So they're going to grab a proton and become protonated. When that happens, now they've lost their net charge and they really want to be embedded more in the membrane. They don't want to be over here by this A subunit. They really want to be in one of these pieces around the side that are fully embedded in that membrane. So these things spin so that this new, newly non-negative, this newly protonated acidic side chain can be in the middle of all of these lipids. Okay, so it moves. And as that happens, right, it brings a new, because this blue piece in the back has been moving, it brings a new one here. A new H plus can come in, can bond to it, it becomes neutral, it wants to move, so it spins further around, and so on and so forth, until finally one of those with the protons makes it over here. But now the channel is to the matrix side. And so if we think about that, in the matrix side, there's really low hydronium. That shifts the whole thing here. That HA is going to want to give up its proton. It's going to want to exist as the deprotonated. So we're going to see it give it up, which makes it negative again. And this is what makes the whole thing spin. Okay, so essentially the protons come into a group. They're picked up by the C ring. They ride it all the way around. So the protons come in, they're picked up by one of these C rings. They ride it all the way around till they're in this channel, and then they exit through the bottom. Okay, so they're pulled into the top, pushed out at the bottom, and it forces the machine around. The number of C rings determines the number of protons required to synthesize a molecule of ATP. So vertebrates have 8, which is the lowest number, making this very, very efficient. If we had more subunits, picture it, right? Every one of these has to pick up a proton before it makes it around here. So if we had more subunits, we need more protons, but every full spin will still only release 1, 2, 3 ATP. So fewer subunits means we need fewer protons per ATP. All right, and then this is just a figure that you can use to kind of try to help tell the story of oxidative phosphorylation. So you can explain the movement of the electrons through the electron transport chain. You can talk about why this is shaped this way. You can talk about the function and how ATP synthase works. And in the next video, we will talk about the regulation of ATP synthase.